All right, students of my calculus course, we are now getting ourselves into an entire new world after we have successfully learned all of that skills regarding taking derivatives. And so here we are at learning what antiderivatives are, and at some point I'm going to start talking about the indefinite integrals. Okay, so now let me move over to my other board for a demonstration example to find out what an antiderivative is. So let's start out with a function like this, and at the very beginning point right here, let's not too worry about the name. So yes, we are about to talk. I'm about to talk to introduce what an antiderivative is, but forget about the name. Let's look at what we're doing first. Let's look at the goal of what we're doing, and once we clearly understanding our goal, then we will start defining a name. So a name, a term is always after we clearly know what we're doing. So let's say I'm going to have a function, function f of x equals x squared. Anyone watching this video should be well familiar with this function f of x equals x squared. It's a quadratic, it's a very simple quadratic, and even more, a little more algebraically, as an algebraic explanation, then this is more like a power function. How's that? Okay, but that's not my point of reminding about what the function is. Now I'm going to raise the following question. Okay, so here's my question. What function has f of x as its derivative? All right, and so at this point, I have all my reason to start pushing your thinking, pushing your thoughts to another direction right here. So we have been finding derivatives all over the entire course. In calculus 1, that's usually a lot of schools have been referring to that. But now the next step after successfully we've learned about taking derivatives, now I'm asking what function has this given f of x here as its derivative? Okay, what function has f of x as its derivative? So to be clear, we are not finding derivative. To be clear, we are not finding derivative, but instead we're actually treating this as already a derivative. Okay, you got my word for that. Be clear with my word right there. We already have this function as the derivative of some other function. So what function is that we're looking for? Okay, so that's why, again, in the wording of my question here, what function has f of x? What function has x squared as its derivative? Okay, and so now, in that way, so at least, and I have to be clear now, anyone arriving at this video and ready to watch it, you must have gone through my other lectures and my complete lectures about all those times we're doing derivatives. And so I expect that anyone watching this video is fluent in terms of finding derivative. And so start having, and there's no method or anything like that yet, no method, and we are at that stage where we're hunting, where we are searching for a method, a solid method. So just keep in mind clearly our goal here is what function. We're looking for that function that has x squared as its derivative. Okay, so here's the thing. If x squared is the derivative, think about that. It's a power, and that's the reason why I mentioned about that a little earlier. If we can recognize the structure of a function, it helps a lot. Okay, so our function here is an x squared. It's a power function generally or algebraically. And so if we want to, so think about those days when you were doing derivative, then if you want to arrive at a derivative being a square, then start thinking. Does it make sense that your function before taking the derivative, does it make sense that your function before taking the derivative must be a power 3? Okay, because the power rule back in derivative days right there, that we've been learning so fluently that The power rule is the famous rule where anytime we're taking the derivative of a power, then we're going to end up with the power reduced by 1. I'm just reminding that. I mean, that's not all about the power rule, but for now, that's one thing, one major feature of the power rule that anyone will remember. Anytime we're taking the derivative on the power rule, the final power in the derivative, in its derivative, will reduce by 1. See, the power started out 3, so now if we want to arrive, so I should have put it the other way around. See, when you're taking the derivative of a third power 3, then we will arrive at the power in its derivative, x squared, as it's 3 minus 1. Okay, so enough reminder for all the derivative math right there. And so now it makes sense now that we're looking for. So now think about the other way around. If we're going backwards, so it's not an equal sign, but I just want to indicate to find that answer, and we're on our work to search. So indicating equal sign is not a good thing. So I just kind of naturally enough, if we're going backward, if this is a derivative and we want to search for that function, I'm right now forced to use this arrow over here. It's not a limit symbol, it's not anything, it's just my own style of indicating that we're searching for an answer. So the answer is which function or what function has this x squared as its derivative. And so it makes sense enough. Now, my bottom line, it makes sense enough that we just simply raise the power by 1. Okay. We raise the power by 1. It makes natural sense. Because now when you take the derivative of that higher power, then we will get back to the x squared. Okay? All right. But now I already wrote that down earlier. So now we're on our way searching, and I'm not saying that this is the final answer. So now let's formally look at this. Let's look at x cubed. If we claim, so we thought we were done. We thought we were done. That from x squared, trying to find the function that has x squared as derivative, we think that it's x cubed. But so now, when you're doing this kind of work, you already had a perfect way to check whether you have found out your correct answer or not. How do we do that? Take the derivative of whatever you think, or whatever we think, whatever I think to be the final answer. So if we think that the final answer is the x cubed, that is that function having x squared as derivative, then let's go ahead and take the derivative of x cubed. The derivative of x cubed is sadly not simply x squared. It's actually 3x squared if we remind ourselves about the power rule that we've learned back then when we were doing, back in those days when we were doing derivatives. Okay, so something is still not quite there yet. Okay, something quite not there yet. And so that means, and now it rings a bell that, hey, if we want to find the derivative, we want to find that the function that has x squared. This is our goal over here. We want to find what function having x squared that has x squared as its derivative. So we're almost there. We search for, it makes sense that we land into an x cubed. But now think about it. We need a coefficient, some kind of coefficient, some kind of value c here, so that when later on when we take the derivative of this to check our answer, it will cancel out with the c here and land back nicely into the x squared, just the x squared. Because otherwise, if it's just x cubed, simply x cubed, then taking the derivative x gives you the extra coefficient 3 right here. And that's not quite our destination that we were looking for. Okay, so in that way, now it makes perfect sense. And the math, believe me, anyone viewing this video should have now strong enough math background so that you can quickly see this in your mind. That I should have, let me now grab a different color marker so that it's kind of catch your attention. We need a coefficient 1/3. Okay, it's just a natural sense now telling me that, hey, it makes sense that we need a 1/3. A 1/3 as a coefficient. Because why 1/3 multiplied with x cubed? All right, so now let's find out again. In what I said earlier, if we now believe that this is our final answer as the answer to what function has x squared as its derivative, then here we go. Let's find it. If we believe that 1/3 x cubed is that function having x squared as the derivative, then let's find out. How do we find out? The only way. Take the derivative of 1/3 x cubed. And so 1/3 is a coefficient. It stays the same according to the days that we've learned all the rules about taking derivatives. And then, of course, we multiply with just the derivative, the power rule itself on the x cubed here. So that gives me 3x squared. And so 3 as the extra coefficient produced by the original power here will cancel with that 3 in my 1/3. And so, bingo, we now do land into x squared. And so, now we found our answer. That searching work has now come to an ending point. So, now I'm telling you, what function has x squared as its derivative? The answer is here, 1/3 x cubed. 1/3 x cubed. Okay? And so, let's try again. Let's try again. I am now going to, and I'm gonna purposely save my empty space on the other board for later on to write down a formal definition. So I'm gonna erase the work here, but gonna leave a certain the main question. I'm gonna leave it here, and I'm gonna erase this work. And what about how about x to the 5th power? Your function is f of x equals x to the 5th power. So, different function, of course. I just happen to use the same name f of x, but I meant to work with a different function. So, but generally, I mean, so far, it's a power function. Okay? And I'm asking that question again. That same question here is being applied to this x to the 5th. What function has f of x, x to the 5th right here, as its derivative? Okay, and so now we already had a little bit of experience after we were doing that x squared function earlier, finding the function having x squared as the derivative. So now we're repeating the exact same question, searching for the exact same kind of answer on this new function. Okay, so x to the 5th, we want to find the derivative before we land into this as the, we want to find that function before we land into this x to the 5th as the final derivative. And so it makes sense that the function before we take the derivative should be, I only say should be, x to the 6th. Makes perfect sense that way. It makes perfect sense that way. Okay? Because when we take the derivative of x to the 6th, the power will definitely reduce by 1, as we have already knew. Okay? But now, outside of that, we actually need 1/6 as a coefficient that needs to be attached to this. Because why? Because now think about it. Well, you can also start verifying my work up here. If I now believe that this is my final answer to that question, that what function has x to the 5th as its derivative, and if I claim that this is my answer, let's verify that, and you can verify me as well on your own work, on your own time right now as you're watching this video. 1/6 as the coefficient times x to the 6th as a power function. Taking that derivative, so this is my verification step to make sure I have landed into the correct answer here. So 1/6 was the coefficient, it stays the same. Multiply with the extra coefficient that came down from the original power if we are taking the derivative on the x to the 6th here, and then multiply with x to the 5th. And so now 6 cancel out with that 6 in the denominator of my original denominator, the coefficient. And so this is now x to the 5th. So we found our answer. We found our answer. So for this particular problem, the answer is, for this particular question on a different function here, that's our answer right there. So now I'm saying 1/6 x to the 6th is that function who has x to the 5th as its derivative. Okay? All right, so I'm going to create quickly one for anyone viewing this video to quickly try on your own. And it's not even a formal example yet, and I did not even introduce any name yet. Let's just stay with this question. What function has f of x? So I'm going to switch to a different f of x. How's that? All right, so here we go. how about f of x equals x to the 10th power. Okay, give it a try and believe in yourself. I know you can do this. Okay, so I'm gonna you can go ahead and pause the video. I'm gonna just wait for about a minute, and then after you come back from resuming your video, I am going to only show the final answer. Okay. All right, so I hope now you're back and had some answer, has at least some thoughts, and be able to verify on your own right here. So the answer to this question, 1 over 11 times x to the 11, and that is our answer. So now I say 1 over 11 times x to the 11 is that function that has x to the 10th as its derivative. Okay, so far we have generally recognized certain things already in our work, but I mean 3 different problems, 2 problems that I worked and I show everyone, I guided away, and then now there's one that hopefully you guys all agree, I mean viewers all agree with my own answer up here. Okay, and I didn't really show the work here on this one anymore. All right, so now let's get to the other board, and it's now time to write down a formal derivative. But I just now realized I'm a little rushing, so let's roll back to the other board. I need to erase this question right here, and so now you see I gave you that function f of x, okay, and then whatever that was, and I was asking this question, I erased it, but I had to write it down simply because I had to rewrite it in a smaller writing so that I can have more space to put in some more explanations. So I was asking what function, okay, has given f of x as its derivative, okay. That was the main question, the main goal right here. And so we've gone through quite a few different problems, right? The first one here, and so now let me put all the 3 little problems we have done together, even though there are not any examples yet. They're not any of the examples I'm preparing that I have for everyone watching this video. But let's say the function we had there, the first try I started out was the x squared function. And so the answer we found there now as a recall again, or feel free to roll back on the video to remind for yourself that the function that we claim to be the function that had x squared as its derivative is the 1/3 x cubed. 1/3 x cubed. Okay, so we went and I used arrow, sort of like it's just because we didn't formally have any work, I mean any symbol for this kind of work. As the instruction for this kind of work, so I just have to use arrow for now. Okay, and so we found that function having x squared as its derivative, and this was the one. Okay, then I guided you through x to the 5th as the function, or we want to treat this as a derivative already, and want to find out what function will have x to the 5th as its derivative. And so our answer was 1/6 x to the 6th. Okay, and so now x to the 11th, I mean x to the 10th was the one that I brought it up on the board, and I left that for viewers or for students of mine to go through and find the answer on your own. And I highly believe that any of you should arrive at the same answer with mine right here, that it was 1 over 11 times x to the 11th. So I purposely put all of these results here on a chart, and with the side by side right here. If we're treating x squared as the derivative, then its function getting this as the derivative, its function that having x squared as derivative is the 1/3 x cubed. If our function is x to the 5th, then that function 1/6 x to the 6th has x 5th x to the fifth as its derivative, and so on and so on. And so now, it's an informal but widely used symbol. So that function that answers this question right here, that function that answers this question, clearly it's not f of x. Clearly it's not f of x. Because f of x here I use a lowercase letter. But the function we found here is that function that has f of x as its derivative. So we have to come up with a different function name, but somehow looks relating to this function. And so, in that reason, mathematicians in many generations have been using capital F. So if our original function is a lowercase f of x, and then we were put into the situation to find the answer of that, the answer to that question, what function has f of x as its derivative? And the answer now, we name the function, those functions, usually the capital function, but with the corresponding letter. So capital f of x here are those answers. So if lowercase f of x is an x squared, then capital f of x is the 1/3 x cubed. If lowercase f of x is an x cubed, x to the fifth, then capital f of x is a 1/6 x to the sixth. And if lowercase f of x is an x to the 10th, then the capital f of x is the 1/11 times x to the 11th. And trust me, you can start pausing this video, dive into a piece of paper and with a pencil and start having fun with this all day long, because it's a very valuable stuff that you have learned just now. Okay? And so out right from this table and putting side by side, and so that you can clearly see the relationship between a lowercase f function that we're starting out and then the capital F version that we purposely name it that way to point out that some relationship. Then the one relationship I'm talking about is this capital F of x is the one that satisfying, isn't it true, that capital F prime must equal f of x? I'll just step out of the board. This mathematical expression is the only way and the best way to describe our answer to this question. We started out with a function notated as a lowercase function, f of x. And the question that was brought to us here, what function has f of x as its derivative? So there we go. The answer is this capital F of x function, because see, capital F prime equals f of x, the lowercase version. Okay, so now we are ready to get back to my empty board here, and now I'm about to introduce maybe for the first time this term right here. So a function capital F of x is said to be now I'm going to switch quickly to red ink, to be the antiderivative, or to be precise right here. So a function capital F of x is said to be an antiderivative. Antiderivative. Okay. So that's the name right there. I'm writing that in red ink so that you can see the word clearly and it will catch your attention. So a function capital F of x is said to be an antiderivative of a lowercase f of x. Okay. If this capital F of x right here, if it satisfies capital F of x equals the lowercase f of x. All right, so there we go. This is our one important definition that anyone after learning all about the derivative work in calculus and ready to step into the next step in learning calculus. Your calculus learning is a long journey. Some universities, some colleges, they break that into three the consecutive courses. Some universities, some colleges, they break that into 4 consecutive courses, and you're gonna step by step go through all of these. So some schools regard to this as the Calculus 1 material. Some other college refer to this as the beginning of Calculus 2 level. So I'll leave that for viewers who know whichever class you're in. But this will never be any different in any course, because this is the only way to define what an antiderivative is. Okay? So again, as a definition, and it's just the way we let it be, the way we name it. So now a function capital F of x is said to be an antiderivative of the corresponding version, but lowercase f of x, if it satisfies this requirement. If it satisfies that the derivative of capital F must land exactly into this. Okay, and so now we can formally get back to the other board where we showed a chart. And so now we can legally have a name for these guys right here. So at this point, I feel now safe to erase this question, because anyone know now that when you're taking an antiderivative, when you're finding an antiderivative to a function, you're just searching for that function having our given function here as its derivative. Okay, and so now this is what we do. So this is if this is function. Okay, if this is just the ordinary beginning function, then this is any of these guys corresponding on the right hand side column is antiderivative. Oops, used the wrong coloring. Antiderivative. All right, so x squared, an antiderivative, and hear my wording carefully, and I'll get back to explain that. So if our function started out at start, or at start being an x squared function, then an antiderivative capital F of x squared is 1/3 x cubed. Okay, if our function here is an x to the 5th, okay, and these are all it's the best function to start our learning about antiderivative is the power functions. And it makes perfect sense with back in those days when we learn about derivatives as well, because of the power rules. So here we are reversing the work of taking derivative. Okay, so if your function here is an x to the 5th, it's a higher power function, then its antiderivative, one of its antiderivative, or an antiderivative of x to the 5th is 1/6 x to the 6th. Okay, and then x to the 10th. Okay, if x to the 10th is the function from start, then it's, or an antiderivative of x to the 10th is 1/11 times x to the 11th. Okay, so that's what it is right for now. All right, so now let me get back on this board and purposely highlight, and I was using that term earlier. So now if you're looking into this definition, a function, any function, capital F of x, is said to be an antiderivative. I'm not wrong about this. Why is it not the antiderivative? But here I'm underlining an antiderivative. I almost wrote down the antiderivative, but actually it's a function, any function, capital F of x, once it satisfies this requirement, right? We call that it's an antiderivative of f of x, if it satisfied this requirement. Okay, so is there a secret out there that's still hiding, that's still being hidden right here? Okay, so let's find out let's unlock that little secret right there. Okay, so let's get back to that. And I'm going to build the chart for here. How about f of x? X squared. So f of x is given to be x squared. Let's find an antiderivative of x squared. An antiderivative Okay, meaning what function has x squared as its derivative. Okay, and so now this is what I'm doing. Capital F of x makes sense that way, right? We've learned the name, and we also learned the formal name, the formal way of naming an antiderivative. Okay, and I keep saying an antiderivative instead of saying the antiderivative. Okay, so x squared, our answer we found earlier, 1/3 x cubed. Yes, that was the answer. I was not wrong, you weren't wrong. Anyone looking at this, we took the derivative, we checked it out carefully, and it wasn't wrong. We took the derivative of this, it landed into this x squared. Okay, nothing wrong with our answer. But now let's look at another one here. All right, and I highly believe you will agree immediately. How about 1/3 x cubed but plus 5? Now I'm telling you that this 1/3 x cubed plus 5, it's not the same as 1/3 x cubed. It has that additional constant 5 here. So that made it completely a different function. But now I'm telling you, this is also an antiderivative, or in other words, another antiderivative of this x squared. Take about 5 seconds pause the video to verify me, because I believe your calculus learning up to this point is strong enough for you to verify what I'm saying. And the only way, anytime that you that you want to verify anyone saying that this is the answer of an antiderivative, you know what to do. Take the derivative and see and find out for yourself whether we landed into that original one. All right. Have you had your answer? I believe you must have had that. So this is an antiderivative of x squared. This is also an antiderivative, and as a matter of fact, this is the most natural one that happens when we were just searching back in the term. But so plus 5 is also 1. So wait a minute. So in that way, it started opening a door for us, because now things can start going a little wild. All right, so 1/3 x cubed minus 1,000. It's also an antiderivative of x squared, because spending a little time taking this derivative or the derivative of this term, and this function here is not any of the other two guys, even though it has some similarities, but in the end it's a completely different function. So we got 3 different antiderivatives so far, and there can be many more. All right, so now the truth is we are ready for our function. So if we're now looking at all these guys together right here, all of these possible antiderivatives, and it's not only one answer, I mean, if we're pointing to any particular one, that's why the definition was saying an antiderivative, because anytime that you land into one particular one of them out of the entire family, it's only an antiderivative of the function. Okay, because there can be more than one answers that satisfy this requirement. Okay, and so now that's why in this way right here, just like that, then we've had it looks like we have one core one, and the rest of the family is just simply a matter of adding a constant to that. Okay, and so in this way, so now okay, so let's say I'm going to put that back, that f of x equals x squared. This is f of x. And then our capital, the most natural one that happens was 1/3 x cubed. Okay? And so now to kind of distinguish, because see, I set this one here as kind of the most natural one, because when I start raising up that question earlier, when I started to raise up that question, anyone's in your work to search for an answer will start thinking of this one. Okay, and the other one comes as a consequence. And so in that way, allow me to use this term. I mean, I use this term. Some other professors I've seen using this term, but not all of them using that term. But every instructor, every professor has his or her own way of interpreting this. But I call this one the one that most naturally happened. No constants added to that. This is called, how about the main? So this here we can call that it's the main. And let me switch to a different red ink right here. So this is the main antiderivative. Okay. The main antiderivative. So now when you hear the term the main antiderivative, you know what I'm talking about. It's just that one that's most naturally happened. Okay? And so now from clearly distinguishing the main antiderivative, so now I can call that the main antiderivative because that's the only guy. Okay? And we have already distinguished that guy out of the rest of the other family members. And so in this case right here, now we can call this, once we've identified things that way, then there's another definition. Okay, then how about I'm going to start out this time in my definition. Let lowercase f of x be a function, just any function. Okay. Then we're going to have the following function. The function capital F of x plus c that particular setup right here. So you see earlier when I was doing scratch work, x squared gives me 1/3 x cubed as one of the antiderivative, and also 1/3 x cubed plus 5. I brought that up, and also 1/3 x cubed minus 1,000. Okay, and so I just now call that particular distinguished guy to be the main antiderivative. So any other guy is generally, and now we can also call it's the function in general, because well it could be different function depending on what value c that is. But now generally my bottom line is any other guy is in the form or is related with the main antiderivative by the anti or the core. Some instructor call it the core derivative, main derivative plus a constant c right here. Okay, and so that's the main derivative plus the constant c. And so now allow me to erase this little reminder right here, and then I'm going to complete my definition. So this function, or the function in that format right here, in that form, is said to be, so what do we call this thing? I mean the whole family of that, instead of just one guy. I mean this is one distinguished guy, we call it the main antiderivative, and then the rest, this is more like a representation of a whole family of derivatives. Okay, so now I refer to this as is said to be the general antiderivative. Okay, of f of x. So the term to be highlighted here, the general antiderivative. So general, so now from now on, from this point on, anytime you're taking derivative, when people just simply say find the antiderivative of a given function, that's what they refer to, the general antiderivative, one expression that represents all different members of a whole family of the derivatives, of the antiderivatives to a function. Okay, and so now in that way we are ready for another formulation. All right, so now going back to what we have done earlier, and we don't need to rush into this learning because I want anyone viewing this video to build a strong foundation before we move on. Otherwise, later on when you get to the more advanced stuff and that requires this basic to be strong right there, then you're going to have to fight hard. Okay, that's always my philosophy right there. And so now, your f of x, if your f of x is simply x squared, and you can apply this after this lesson, this video lesson, you can do that to the other tryouts that I brought up earlier as well. But so now, let's say our lowercase f of x is the x squared, then the work earlier was asking for finding the, then maybe I said a little, I let the viewers into a wrong the way of saying, so how about let's put it this way, if f of x equals x squared, for example, that's the work we did, then now we can say that capital F of x equals 1/3 x cubed plus a constant. This is right out from the newest definition we have. And so this thing here, okay, that thing is the derivative. I mean the antiderivative. All right, or officially this really means the general, but a lot of time. So in my formal definition, I use the term formally, the general antiderivative. But now informally, when it rings to your ear that find the antiderivative, when people specifically say find the antiderivative, that's the one. It's the whole family of antiderivatives. Okay, it's the antiderivative. And so now this, from now on, for the rest of your learning time right here, with beyond taking derivative, then anytime you're asked to find an antiderivative problem, right, then your final answer must have a plus c right here, because that plus c is indicating that you're not only landing into one particular answer, but you're landing into a whole family of answers. And so originally this was the general antiderivative, but now we just, for short, call that's the antiderivative of the function. Okay, and so let's now look even a little further, and we're going to keep exploring more useful learning or understanding. All right, so now I got to make this clear. It's only for the convenience of running symbols. So I'm going to introduce this. In my teaching experience for calculus, a lot of times students who enter this class usually had some experience in high school, APE calculus, or something like that, and some of you have seen that. So instructor there, I don't really mean to offend anyone, but a lot of instructors are going quite different ways with how I approach this. And so when students see this symbols, they're going to start saying, hey, it's the integral, whatever. I introduce that symbol, but I don't want you, or how about I want you to wait as far as you can until I say yes. For now, I only introduce the symbol as a way to instruct viewers, to instruct students of mine to find the antiderivative. So your function, let f of x be a function. Okay, so I introduce this symbol. So this is what the symbol comes right here. So that's why if you start mixing with some of your past experience, maybe you have done some calculus before you viewing this video and have seen that and heard of that name somewhere, I can't stop you from calling that, but I want you to set you into the right understanding. So how about I highly recommend treat the whole package here. You see how I circle in red? The symbol here comes with the dx. Okay? I want you to treat that whole thing as one symbol. But what's the purpose of that symbol? This symbol is an instruction to tell you that the representation, for now, representation of finding capital F of x, the antiderivative of f of x. You see, it saves a lot of wording, the advantage of introducing the symbol, even though I don't want to mention any formal name. So if you're really asking me, Mr. Dung, at this point, if you're viewing this video, Mr. Professor or Mr. Instructor, what do we call this? Don't worry about that. You only see the symbol attached with the function here. It tells you that instead of me telling you find the antiderivative of f of x, find the antiderivative of x, and think of the amount of time I have to write it down in words right there, it takes a lot of time. So one symbol tells you that we are looking for the antiderivative on behalf of that function f of x. Okay, so let me explain a little further, but see, the reason I use the dx here, it's an indication. It's an indication that your final antiderivative is in terms of the x variable. You see, your function in the beginning here was in terms of x. And so I also want to take the antiderivative in respect to the x variable. That's why this symbol comes with the dx as a whole package, as one symbol. I keep using that word, the whole package, because that and with the dx as one symbol, it means two things. Find the antiderivative in respect to the x variable. So I'm expecting that when I'm seeing this symbol, I'm expecting that my final answer is another function in respect to the x variable. And that's the whole idea right there. Okay, but if you have learned something else otherwise, the point now is I want you to set you into that proper way of seeing this, and I'm trying to also align you with the historical development of that big idea of integrals for later on. So don't try to rush yourself. Right now, if you're learning with me and really want to study with me, I want you to take this only as a symbol for now, to take that when that symbol applied to this function, it means find the antiderivative of f of x. Okay, so now after the usefulness of being so clear with that symbol that I introduced, so that now we can start speeding up the process by, I'm going to start introducing for you the first rule we've learned. All right, so this is how I'm using that symbols here. So you see my function, I started out now if we're sort of like rediscovering the whole problem from A to Z from the very first question I brought up. X squared is my function. And so now I see this symbol, that symbol on top of x squared with the dx. Now it tells my viewers, it tells my students that, hey, find the antiderivative on that function. Okay, understandable enough? Maybe let me repeat one more time. This symbol together with the dx symbol as one package symbol tells viewers and tells my students that, hey, find the antiderivative on that function. And of course, at this point, we are already clear. It's intended for the general antiderivative. So what was the answer for that? So it's not only 1/3 x cubed. That was only one antiderivative among infinitely many others. So the legal correct one now is a plus c, because it could be a plus 5, it could be a plus 10 here, it could be a minus 1,000. Okay, but see, now we've done taking the antiderivative on that function in respect to the x variable. See, our final, you see there are two letters here, right? But we treat the other one outside of the x variables as constants, or any other thing as constants. This guy right here is our main variable. Why is that? Because from the beginning, this symbol was indicating that we're taking that antiderivative, and our final product here is in terms of the x variable as instructed here. All right, so that's the idea for that. And so now, as I said further, let's summarize, or let's discover what we did there in a new point of view with the introduction of the new symbol here on top of that. So I also did x to the 5th. I started out introducing finding the antiderivative on that function. So earlier it was just only one antiderivative if we can find it, right? But now we know that this guy here, once we found the antiderivative, we land into a whole family of antiderivatives. And so this is 1/6 x to the 6 plus c. Okay? And the next one that I left for viewers to try on your own, it was finding the antiderivative of my function. See, these two symbols always come together as one whole package. It's one symbol indicating find the antiderivative. And so our answer there, actually, I believe I remember incorrectly. The one I left for viewers and my students to try was to the 10th. Okay, so x to the 10th, finding that antiderivative gives me 1/11 times x to the 11. But now don't forget, as at this point, once we're clear, plus c. All right, and so now the rule and the formulation that I was talking about is here. Let me now quickly erase my board. All right, so one fundamental rule we've learned so far. And that rule right here is concluded. Really, we've done quite a few, we explore a few, and then we come up with a generalization. So here's a generalization. It looks like, so far, the one that I brought up, all of those I brought up, they started out being a power function. Power 2, power 5, power 10. Okay? And so after we found the derivative successfully, we always, the rule of thumb ended up with the power exactly 1. I mean, added 1 after that original power. So here, 5, if it was 5, our final answer is 6, right? 5 plus 1. If our answer here is 2, our final answer for that in the antiderivative, 3, because 2 plus 1, and so the same with that. And so now, the generalization that I was talking about is here. Taking the antiderivative. Okay, that's why I said now you're going to start feeling how inconvenient that is. Instead of me saying it in words and writing it down in words, taking the antiderivative on any x to the nth function, it's a power function. Okay, taking the antiderivative of x to the nth. What can we formulate here as a general rule? And now users and viewers can start seeing it. Students of mine can start sensing it. Well, our final answer has to be x to the n plus 1, obviously. Okay, and outside of that, so we raise the power by 1. Completely opposite with taking the derivative. Taking the derivative, we subtract the power by 1. Power originally minus 1, but here power originally plus 1. Okay, so, and then, but that's not the only one. We multiply with n plus 1. So that's just the main antiderivative. So as the general antiderivative, we plus c. Ladies and gentlemen, this is I also call this the power rule. But let's be specific for those who have already learned through calculus 1 primarily, or the calculus that primarily dealt with derivatives. Then this is power rule, but not derivative power rule. This is the power rule for antiderivative. The power rule for antiderivatives. Okay, and that's why we're of course now in the topic of learning about antiderivatives. So I highlight the term power rule here in capital, but the other one, of course, it's for antiderivatives. Okay, because we're not looking at derivatives, even though it's related. Okay, so that's the first rule that fundamentally we learned right here. But now, this rule has a little limitation. This rule, the power rule that for antiderivatives I just now introduced, We haven't seen that limitation yet within the problems we've done, because any of those we've done had an answer for us, but this rule has a limitation. This rule, formally as a rule now, only works or only valid for the power n. So now I highlighted that for me. Only valid for n is other than -1, and we will investigate that. We will find out why later on. Okay, so anywhere outside of power -1, then this rule will work just fine, perfectly good. But when it's n equals -1, the power equals -1, it's going to have to be something else. And we will overcome with that limitation as well. Okay, but it just don't use the power rule for n equals -1. All right, and so now once we came up with that finalization of the general power rule right there. All right, so it's time to start looking at a couple of basic examples here. And as I said, very basic example. I just want to reinforce your understanding by far. So nothing to be worried about, nothing much to be worried about. All right, so right from the power rules that we have learned, there can be a lot to be done already. See, so this is the power rule. Anytime that you recognize your function is in the form of a power function, then we can start doing a power rule for antiderivative. So I'm now going to call that example 1. And I mean the only instruction of that. Find, okay, find. And so find what? Part A. Okay, just out of my own creativity, about power 99. Any power, it's a power. It works just fine. But now find what? Find this. Find the antiderivative, okay, of the function, of the power function x to the 99th. Okay. Power rule is going to be applied quite straightforward here. See, x to the n. So taking the antiderivative, we're going to raise the power by 1, add 1 to the power, and divide and multiply the whole thing by 1 over n plus 1. Okay, so in that way, here's how I'm, and see, one step, no need to shop around for anything like that. So as far as written work, it's pretty simple. X to the 99 plus 1, so maybe for starter, I'm going to highly recommend doing this. 99 plus 1. I mean, it seems ridiculous right now, but I have a good reason for doing that. So 1 over 99. I mean 1 over 99 plus 1. Okay, so I sort of like copy verbatim the power rule there. And don't forget, plus c. Okay, and so 1 over 99 plus 1 is 1 over 100. So that's our final coefficient. Our function here as a power function is x to the 100. Okay, plus c. There you go. So maybe the most 2 steps, because I was a little picky. It's for your own good. I want you to be as specific as possible. So get for yourself in that habit of, get things done carefully. It can take a little more time, but get things done carefully, and it's easier for you to keep track of your work and trace back where the error came from. Okay? All right. Let's look at part B of our example. All right, so now you can start bringing out as much experience you have had back in your days, your calculus days, learning about taking derivative, specifically on the power rules, because this is what I'm talking about 1 over x to the 5th dx. Okay, so this is not x to the 5th. No, it's not. It's 1 over x to the 5th. And so what are we finding here? We want to find the antiderivative coming out of this function. Okay, so now I'm going to have to apply a little treatment, because see, this function at first sight looks completely out of ordinary, out of standard, I mean, our standard here is we need to see our function as a power. Are we having that yet in the function? It's only 1 over x to the 5th. It doesn't look power. Maybe there's a power in the denominator, but in the end, it's not x to the n power. So here's your trick. Again, this step following it is not the antiderivative work yet. It's only the algebra treatment. Okay, that's why I'm gonna rewrite. Okay, so one symbol, but the main function as our target here to find the antiderivative, I'm going to rewrite it as x to the minus 5. And this is the experience I said about, you can bring it out from your old days learning about derivatives back in your earlier days of calculus. Okay, so 1 over x to the 5th is the same as x to the minus 5. This is now in our ordinary form, or in the standard form. See, now we're in x raised to a power. Okay, and let's check a little bit. The power now is a negative power. That's fine, but it's not a negative 1 power according to the critical limitation of this power rule. So we're completely safe. We are completely safe. And so now we are ready for taking the actual derivative. I mean antiderivative. See, even I mix up sometimes. So x, just writing it, the power rule says from the original power, I'm going to add 1. That's why I want you to clearly write this down. I mean, when you yourself as the beginner, I highly recommend doing this. And then one day when you're fluent enough, you can start being a little skippy in your steps. Okay, so negative 5 plus 1. And then produce a 1 over negative 5 plus 1 in the denominator. Okay, and plus c. That's your starting, but it's already done with your antiderivative. And now I also have to be clear throughout my years of teaching calculus. Now, sadly, many of my students, so I point this out here in this video so that none of my students will fall into that mistake again, that pitfall right here. But you see, recall for yourself that I said earlier, this symbol here is the symbol as an instruction telling you to find the antiderivative of this. So when I advance to this point and the symbol is still there, meaning we have not found our answer yet. Obviously it was like that because when I came to this point, I did not find the antiderivative. I only rewrote, I only re-expressed my function. But now, from that step down to that step, over my years of teaching experience, I keep seeing students mistakenly put that together with the answer. Please do not do this because remember, if you are still having that around and viewers or readers of your work will understand that you are going to take another antiderivative, which is not correct any longer. Because without that symbol, it means you have already arrived at your answer. Your question was asking, find the antiderivative to that. Here's your answer. So you don't need to have that symbol anymore. If you're still having that there, if your instructor is picky, you're going to get points docked up for that. But if you're giving that to a reader who reads your paperwork and seeing that, it's going to be misleading. It's going to make the readers feel that you're going to do another antiderivative afterward. Okay? And so that's very dangerous for your work. And anyone arriving at this video, you're on that way to become, who knows, one day a formal mathematician. So have a sense about being as clearly in the way how you document your work as possible. So every step connects with the previous ones. Okay? And so now, so you already found your answer. So that's why I don't put my sign there anymore, my antiderivative symbol there anymore. 1 over, well, negative 5 plus 1 now is easy enough. 1 over negative 4, so I can have a negative 1/4. How's that? Okay, and then x to the minus 4 power plus c. Now we have our final antiderivative for that. Okay, all right, so let's look at another one. So now, and I have a reason to leave the other board there so that I can keep swinging back and forth to keep reminding people about the power rule. So let's not erase that. I'm going to keep erasing out my work here. All right, so how about a little one for viewers or students of mine to try on your own? So how about an FYT? And again, if anyone studied with me throughout the whole calculus for derivatives and all that, the whole course in calculus for derivatives, and then as I said, many schools, a lot of schools call that calculus 1, then you're going to learn from my style here that an FYT means a problem for you to try for your own trying. I learned that style from my favorite professors back then at graduate school. So now, how about for you to try? I want you to find the antiderivative for 1 over x to the 7 power. Okay, so all this here, don't use any fancy name that I have not taught within this lesson. This is nothing but just find the antiderivative of that. Okay, so it's an FYT, so I'm going to just wait here. Feel free to pause the video. Okay, have your own thoughts on that. Okay, and then I'm going to, once you resume, you're going to see me just giving in the final answer. All right, so I hope you have already had some work and your final answer here hopefully agrees with mine. Okay, so this should be a negative 1/6, okay, times x to the minus 6 plus c. And as far as final answer, I'm happy with that. Many professors should be happy with that. Okay, now algebraically you can also rewrite that as, I should have also mentioned that, I could have also mentioned that back in the part B of our earlier, that we have done earlier. So this is the same algebraically as negative 1/6 times 1 over x to the 6 plus c. So the best way of writing, another way of writing that, negative 1 over 6 x to the 6, okay, plus c. All of these different ways of writing that, but very common in these days that professors allow their students to write the final answer of the antiderivatives like this. Okay, in of course with the negative rules, with the negative powers. All right, so that for an FYT, all right, so now let's look at question C right here. So now let's look at, what about fifth root of x dx. Okay, again, this is another function that looks quite, at first sight, quite out of ordinary, because our rule, the only rule we have learned so far, is the power rule. Okay, and we must see in the form of x to a power before we can apply our rule. And unfortunately, that rule is not shown clearly here yet. Okay, and so we're going to have to play a little, do a little treatments, algebra treatments. And so again, another thing for you to watch about. See, in my next step, as I said, I'm only doing an algebra treatment before I actually find the antiderivative. So of course, it still has this symbol. Okay, the problem still has that symbol, because after I apply the algebra treatment on this, then it will be taking the actual antiderivative is the next step. So recall for yourself, any root is the same as x to the 1 over n that we have learned, and hopefully anyone arriving at this video has been quite familiar with that kind of work back in your days of doing derivatives. And so now I'm rewriting this fifth root of x as x to the 1/5 power. Okay, x to the 1/5 power. So let me make my power a little more careful. So x to the 1/5 power. Okay, and so now x to the 1/5 power. Now you are clear. Now it is so clear that we are in the form of x to a power. Our function has now been re-expressed as a power of x. And so in that way, now it comes the answer. So remind yourself, at this point, you don't need that sign anymore. I almost accidentally say the name of that, but let's be patient. So x to the 1/5 plus 1, okay? That's why I highly recommend doing this, because trust me, there are viewers out there who view this video. There are students of mine who view this video still feeling very reluctant to adding and subtracting fractions. So write it down like this. It will make you add better. It will make you add and subtract fractions better. Otherwise, it's easy to make mistakes. I make mistakes with adding fractions too. So writing it down, as clear as you can is always the number one key. Okay. And so now, after that, don't forget 1 over. Well, we can write it small, 1/5 plus 1. So it's a fraction. 1 over the whole 1/5 plus 1 is in the denominator of that overall coefficient. Plus c. Okay, so, but of course, I don't think any instructor is going to be happy with the students, with a student presenting the final answer like this. So let's move on a little more. Even though this point is officially your antiderivative, this is already your antiderivative, so you don't need the symbol and the dx thingy. Okay, but well, so let's do a little math right here on the side work. 1/5 plus 1, right? You know what you do. Okay, so it gives you a 6/5. That's your final power here. Okay, and that means this number is going to be also placed down here. So now you have x to the 6/5 plus c, and there's 1 over 6/5. Okay, so at this point there's a 50-50 chance that your instructor is okay with this form right here. So for best guarantee, how about rewrite that overall coefficient here, because it's a 1 over 6/5. As I said, it's a 50-50 chance. About 50% of instructors are okay with that, and the other 50% of instructors out there are not okay with that. So how about that's the same as a 5/6, right? Times x to the 6/5 and plus c. So now this is the happy ending point right there, and that's our antiderivative. All right, so now and I understand that usually in my teaching experience, I mean everything I'm saying on the board in a video lesson here comes straight out from my teaching experience with this kind of stuff. And so let's do another problem where it involves the roots and all that. So we're still in example 1. And I'm still going to lead the way, so it's not an FYT yet, even though I know maybe some viewers out there who are so eager for an FYT on your own already. You can also create an FYT on your own. So question D. What about find the antiderivative for, how about, see, x squared times cube root of x. Okay, x squared in product with cube root of x. I purposely brought in something that looks kind of wild, okay, so that after we got through, you will learn some experience, you get some good experience out of that. Okay, so again, I also need to be clear. I pointed out that there's a product here, but it's time to tell you that anyway. So the only rule we have learned so far is the power rule. And if you see me teaching a face-to-face class, I would tell this exact same thing. There are no product rule when you're taking antiderivative. And I mean no product rule here. I mean, you see, back in the days you were doing product rule to take the derivative. There was a rule that directly handled the derivative on a product. We cannot, I mean, there has never been a rule that directly handled the antiderivative on a product. Because the reason I say so, the reason I said so, because there's a product here, so maybe some viewers may try to rush ahead of me. It happened to my the face-to-face students as well. So try to rush ahead of me and misleading yourself into an off path like that. Okay, so So now, as I just said earlier, there are no such thing as a product rule for antiderivative. So there are no product rule equivalent to those product rule back in derivatives day. So the only rule we've learned so far is the power rule that I keep swinging back and forth on the two boards right here. So you gotta use your algebra. There's no way to run away from your algebra. So I set this to my calculus 1, and now if this video belongs to a calculus 2 class, meaning your learning has become already a little more mature right there, but I still gonna tell you the same. I'm still gonna tell you the exact same thing. You gotta get your algebra going, okay? So now this cube root of x, we can use that little reminder here, and I still have that on the board. So the next step here is just the algebra treatment, the algebra re-expression. So x squared in product with x to the 1/3, how's that? Okay, that's how we recognize it. And then I'm not happy with that form yet, because still right now it's a product of two separate powers, and we're stuck. Because as I said earlier, there are no product rule. Okay, so in that way, but gladly for us, we can combine this. See, same base, powers, two different powers, but same base. So 2 plus 1/3, you can do that little math right there. And so now I can rewrite that. So that's just a reminder, but allow me to assume that my viewers here already know how to do this. So I'll leave that for any of you to quickly get that. So all that together is written as one base, x. See, common base, so that common base is here, right? And 7/3, okay? Because 2 plus 1/3 is a 7/3 dx. Now you have landed yourself, see, and the taking antiderivative symbols stays with you the whole time so far, because none of these steps is the step to take the antiderivative. So that's why we got to keep that symbol there, okay? Now once we have landed into that step, then we can find out for ourselves that we have already properly aligned ourselves with this power rule right there. Now we are ready. And again, throughout all of the example questions so far, we never so far ran into that critical limitation where our power was a -1. So we've been good. We've been good. Nothing bad. Okay? And so now we are ready for antiderivative. X to the, again, for starter, I highly recommend to the power 7/3, 7/3 plus 1. Okay? And then there's 1 over the whole 7/3 plus 1 being written there. Okay, and my writing does look a little too tight right there. I'm sorry, my board space is a little tight right there. Okay, plus c. So now at this point we are officially done. I mean, we're legally done with the antiderivative, but I'm pretty sure there will be many instructors out there who do not like this way that a student's presenting to him or her this form. And so we're going to have to use some algebra. So starting at this point, we no longer need that symbols. Okay, and for the later steps, we no longer need the symbols. And so how about I'm going to make that extra space right here to continue from this step, because I know I'm short of space here. So 7/3 plus 1. 7/3 plus 1 is going to be, well, do a quick math right here. 7/3, right, plus 1. So that makes it 10/3. Okay, clear enough? All right, so now in that way, knowing that for clear, then now our final answer is x to the 10/3 plus 1. It's a power. And then 1 over, actually it's not plus 1, I apologize, plus c. And then times 1 over 7/3. And then at this point, there's still about a 50-50 chance that some instructors do not like this final answer, final expression. And so I just want to show viewers, show my students the best final answer that any instructor won't reject. So x to the 10/3, I mean, and this is supposedly right from the beginning here, it should have been 10/3. So now it should be 3 over 10 there, and then that's the coefficient. Algebraically flipped upside down, and and then this is 10/3 plus c. We are now done with our final antiderivative, and that's the one that nobody can reject right there. Okay, and so that's pretty good for this one, right? All right, so now let me produce another one. And so now when it gets to this point, any students, any viewers who already had good experience with handling these, then you can skip some of these examples as well. You don't have to go through all of my examples, every single one of them, and then maybe you're going to have to spend too much time, as my video is going to get lengthy anyway. So part E, okay. So what about just 1 over, so how about x square root x dx, okay. And so again, this time we got things in the denominator. There's a product in the denominator, okay, and then it's a product here, and then there's root involved again, and some non-root. This is power 1, this is power 1/2. So see, square root of x is the same as x to the 1/2. Just a reminder, okay. And so in this case right here, algebraically, in my next step, how about I should write the algebra step here. So that means as long as we're still doing the algebra step, we got to stick with that symbol. So now it's 1 over x, but in product with x to the 1/2. How's that? Okay. And then, now we've learned the work similar to the prior, the earlier example. We're going to have to apply one more algebra step right here. See? Same base, and I'm talking about focus your attention to the denominator here. So same base, power 1, this is power 1/2, so we can total up the two powers. So now it's going to be x to the, see, 1 plus 1/2 is going to give me a 3/2. Allow me to assume again that my students, my viewers viewing this video are already fluent with these fraction skills somewhere, right? At some certain decent level of working with fraction, and then dx. Okay, so now the next algebra step. So any of these steps it's just a better treatment algebraically. So I still need to stick with that symbol there. So now x to the negative 3/2 is here, dx. Okay, and now in that way, now we are ready for the final answer. So maybe I need more space in that, so I'm going to write it starting from this line right here. So x to the negative 3/2 plus 1. That's for my power, the new power, the power of the antiderivative is the original power plus 1 according to the power rule. So I highly recommend doing this, adding it out carefully. And then 1 over all that negative 3/2 plus 1, okay, plus c. And so now, nobody need to rush here. If you feel uncomfortable with doing this, pause the video, pull out a piece of paper with a pencil, do the math here formally. Otherwise, in my next step, when I throw in the answer, you're going to feel a little shocked right there. Okay, so I don't want that to happen to any of my viewers. So go ahead and do the math here carefully, and you can resume my video. All right, but so in the next step, my adding of the powers is going to give me, for the powers here, negative 3/2 plus 1 is going to give me a negative 1/2 power. Okay, negative 1/2. And then so in that way, I am going to have a 1 over the fraction, the little fraction, negative 1/2 in the denominator. Okay, because all that here, the new power will also stay in the denominator of that final coefficient. All right, so now plot C. And so, as I said many times throughout the past problem, there are still about 50 chance that your instructor doesn't like this final answer. So let's just, and the little step is left over is small enough, so I can just write it on this board, and I'm not going to erase this. So now we can go your final answer here, and we don't need that antiderivative symbol anymore. So it is now going to be minus 2 times x to the negative 1/2, okay, plus c. That's your final answer, okay? All right, so that's a good amount of problems on the very basic applications of how we can apply it in a different creative way. And of course, up to this point, I have to admit I'm out of creativity because at least for these basic line, basic problem along this line right here, then those should cover enough, and you should start drawing some experience out of these problems right there. And now, let's quickly look at example 2, which stands as one example on its own right here. And we're going to find out a couple of things. Okay, so let me get straight to the point right here. Example 2 is one example, but I'm putting that here as an example where we do and we explore things. We work it out, I guide the way, and then we're going to explore things. So, just like example 1, there's only one problem though. We're going to find the antiderivative, and I purposely put you in this situation. Let's find that. Okay, let's find that. Okay, wait a minute. Isn't it the one that's not that is forbidden? We run right into that problem where the x to the n and n is the -1 power. So don't back out. I want you to also understand why it's forbidden. Okay, let's find out. And it should be simple enough to understand. Well, because if we just brutally apply the product rule, the power rule here. The power rule says -1 as the original power plus 1 times 1 over -1 plus 1 and plus c. This is why. This is why it has been a critical limitation right there. We can't apply because it's just the math that we, the human on Earth, are doing. We can't overcome divided by 0. We can't. We have never found a way to divide by 0. Okay. So I used to make this joke with my face-to-face students right there that as long as you are still a human living on Earth, you can't divide by 0. So anyway, so that's the reason why. But now that doesn't mean we're going to quit. That doesn't mean we're going to stop doing the problem and let's go home, forget about it. Nope, it's not going to happen that way. We're the math people. We got to find a way to overcome our own limitation. Okay, so my recommendation. Do you recognize x to the -1? At least roll back on this video and search throughout example 1 right there, throughout the problems we were doing in example 1. I've had tons of examples where it had something similar, something that relates with the negative power. Okay, so the negative power is recognized from something like this algebraically. So algebraically, x to the -1 is the same as 1 over x. Okay, it's 1 over x. Is 1 over x, and we want to find the antiderivative of this. Please forget completely about the power rule. It didn't work. We just showed it earlier, and that's why we purposely rewrote our beginning expression in this. Take a moment to see if you recognize this from your days doing derivatives. Okay, and again, remind from the beginning of this video lesson. The whole point of doing antiderivative is that we have that question for ourselves. If this is our function f of x, what function has this as its derivative? What function has 1 over x as its derivative? Isn't that the natural log of x? Because back in those days when we were doing derivatives, then derivatives we learned formally. The derivative of natural log of x is 1 over x. And now this is simply, so it's just a matter of who remembers wins. It sounds like ridiculously a joke, but there was no method. It's just a matter of remembering your stuff. But trust me, as you've gone through your calculus 1 or your days learning about derivatives, then you will see that kind of work enough to the point that it will stay with you, and it still carries with you until now. So that means what you answer here. The antiderivative of this guy is the natural log of x plus c. I will get back to explain a little more about this, but Now, when we're starting to do antiderivative, and as I said, I don't want to get too far into that here. In some other videos, I will explain. But taking the derivative, you don't need to worry, just natural log of x, and then you take the derivative, it gets you 1 over x, simply just that. Okay, but now in our work here, we're going the reverse way. Please put that in absolute value for me. Okay, so anytime we're taking the antiderivative of 1 over x, your antiderivative will go in natural log, but not just simply x, natural log of absolute value of x. That's the one thing for sure. Okay, and so that's your answer. All right, so that's your answer. So all of a sudden we realized a little thing for here, and now let me move on to the other board here. Example 2 was standing on its own here. It has its own impact, so it became a rule on its own. A rule on its own. Antiderivative of 1 over x equals exactly natural log of absolute value x plus c. Please nail that down for me. Okay, and I'm not really forcing anyone to memorize this, but trust me, as you've gone through and seen it enough, as you're going through and seeing it often enough, it will stay. Okay, so we've learned another little rule right there. Ready for third example? And another easy one, or maybe another one that stands on its own. I shouldn't say easy. It depends on how we see it. All right, so now how about let's find the antiderivative of e to the x. E to the x. Exponential function, but base e specifically. So what function has e to the x as its derivative? Okay, take a moment to think. So isn't that just the e to the x itself? Okay, because back in the days when we were taking derivatives, taking the derivative of e to the x is e to the x. And so now, surprisingly, taking the antiderivative of e to the x, it will get you into e to the x. Okay, but don't forget plus c. So it's a little different with an extra constant for whatever it could be. We found it. Okay, so because, see, how do we know that's the answer? And I should have also done this for any of the steps we've had earlier. So the reason I know that this is the answer, because, see, taking the derivative of this, right, equals e to the x plus derivative on a constant is a 0. So it's just that. That's why. Okay.